The opponent, what's the question, the problem you would like to challenge the reporter?
We would like to challenge problem 4, choosing rubber band.
Okay, they would like to challenge the problem number 4.
Reject.
Then we would like to challenge the problem number 15, West Row.
Reject.
Then we would like to challenge problem number 16, Fashion Cancel.
Reaccept.
Oh, so please write your name for who are going to get the ball.
Greetings, honorable judges and fellow contestants. Today I'm going to present cushion catalogs. I'm Justin. So this is our outline. So it includes public statement, demonstration video, theory and hypothesis, then experiment setup, and experiment and conclusion. So this is the public statement. Place an object on a large cushion and drop several other objects in such a way that the first object is catapulted away. Investigate how the exit velocity depends on relevant parameters. So our main focus is exit velocity and relevant parameters. So this is the demonstrated video. So as we can see, when the ball falls, so I'll just tell you about the experiment. So when the baseball falls down from here, it would bounce, it would hit over the cushion. Then the marble over here, which is over here, right here, would catapult it away. So it would look like this. There's a marble. And so this is our experimental setup. So this is our brackets, and this is the tape ruler that we measure the height. And there's a baseball we used, and there's a marble here, and there's a cushion. And then we use this camera to record the whole process. And we have a computer here, and we use tracker to track the motion of the marble and the motion of the baseball. Oh wait. And we have a claw over here so that we can control the height. And so actually our theory consists of, we have two theories. So this is the first one. So I'll start. So this is our, so when the baseball collide with the cushion, it compressed the air in the cushion, and then the air will flow to here, this volume, and the risen height equals the volume over here. But we don't know, when we look at the shape that it collides, we don't know what it is. So we assume that it is cylinder. And so we can use this formula. And then, because during collision time, P left equals P0, which is the atmosphere, times plus the collision force the baseball applied, and the space itself, the space of the baseball itself. And during collision time, at that moment, there is a pressure difference between P left and P right. So then we calculate the delta P. And so we calculate the work done on the ball so that we can get the height. That the marble flew. And this small m is the weight of the mass of the marble, and big M is the capital letter M is the mass for the baseball. And delta H2, H2 prime is the height that the marble catapulted. And this H is the this capital letter H is the height the baseball is dropped from. And this small h is the height of the cushion. Next. And so this is our second theory, which is standing wave. So when the baseball collide with the cushion, it looks like I'll talk about the theory first. So we use standing wave to explain this phenomenon. So we use this formula so we can get the velocity of y. So then, because it's a wave, so the definition of wavelength is k equals 2 pi over lambda, and then we can get k equals n pi over L, and n is a natural number. And so and then we calculate the amplitude of the wave. And so because it is easier for us to measure the height, and we can convert height into the exit velocity. So that in the whole experiment, we use height of the marble catapulted to present the exit velocity. And so the height is, so this is the formula for the height. So we have 3 experiments in total, and this is the first one. So in the first experiment, we control the initial release height and the distance between objects. And then the independent variable is the saturation of the gas of the cushion. So this is actually the saturation should be like 0%, 20%, 40%, 60%, and 10%. I mean 100%, sorry. 20, 40, 60, 80, and 100% saturation. And so it looks like this. Wait. And so we can get our greatest rebound height is 70%, x equals 70%, which reached 76.8 centimeters. So you can see from the previous page, we can see that from the data, there's actually a peak like this. And so we're going to explain why it decreased so significantly. So when the saturation is very high, it's hard to compress, which is difficult for the cushion to create a standing wave. And in lower saturation, there is not air enough to be compressed to create a standing wave. And this is our experiment 2. Our control variable is saturation of gas and initial release height. And our independent variable is distance between objects, from 10 centimeters to 30 centimeters. And so actually we draw lines on the cushion so that we can calculate how the distance between the marble and the baseball. So we can see that when we place them on either side of the cushion, 10 centimeters, we start from 10 centimeters to 30, and we can see that we have the peak over here, these 2 peaks, and which means it's the antinodes of the standing wave. And our estimation of this wavelength is 22 centimeters, which is these 2 subtract each other. Oh wait, it's not subtracted, sorry. There's another formula for this. Yes. We're looking, because of the material of the cushion, you can see that when it collides, it creates half of a wavelength over here, and then but the material of the cushion held it from pumping up. So that results in energy consumption, which the antinode is flatter. So it actually it cannot actually catapult it very high. So this is our 3rd experiment, which we controlled the saturation of gas and the distance between objects. And our independent variable is initial release height. And so we can see that this line is our theoretical line, and this one is our experiment data. So we can see that there is a positive correlation between the rebound height and the initial height. Discussion. For low initial heights, it can lead to longer impact time, which allows the marble to slide away. So so that it won't catapult away. So conclusion, we can come to a summary that compressed volume causes the surface rise of cushion, which does work on the marble. And second, position of the marble on standing wave affects rebound height, which we can transfer to exit velocity. Third, this saturation for rebound height is 70%. Fourth, the wavelength is approximately 22 centimeters. Fifth, positive correlation between rebound height and initial release height. Thank you for your time.
Thank you very much. So the appellant, please take the stage, ask quick questions for 2 minutes.
So first I would like to ask about, because I see your cushion doesn't have a flat surface throughout the cushion. Do you think that the part when it's bounced up and bounced out affects the whole phenomenon?
Can you say it again?
I mean your cushion, there
Yeah.
is some kind of wave-like structure. Do you think that affects your phenomenon?
Yeah, of course.
Did you consider that in your theory?
You mean
The cushion you use, there's a certain wave-like structure.
yes.
And if you place it in between those two notes, and does that affect the phenomenon?
What do you mean two notes?
Next question. I would like to ask, because you use height to derive the
Yes.
initial velocity, am I correct? So when you're deriving height, I assume you use energy conservation law. Am I correct?
Yes.
So do you consider the air resistance of the ball when the ball is launching catapulted through upward?
No, because the marble is pretty heavy. And,
Okay, so I think you use the wave to explain this phenomenon, and you explain the standing wave theory. So the standing wave should be consist of the waves that's going through two ways, like in the left and the right. Am I correct?
yes.
So have you considered this wave, the energy of wave, as a proportional relationship between these two waves?
Actually, I don't think so, because when it rebounds, the marble is already in the air.
Okay, so do you consider that, because it actually spends time if this wave has to collapse to each other to become the standing wave. This time gap, do you consider this time gap as a relevant parameter?
Okay, take 3 minutes here.
honorable judges and worthy opponents. This is me to opposing problem 16, cushion catapult. So for the problem statement, you place an object on a large air cushion and drop several other objects in such a way that the first object is catapulted away. So the reporter focused on analyzing the x velocity by using the height of the ball to derive the x velocity, and also examine relevant parameters. So for the summary of the report, after explaining the phenomenon, the reporter first analyzed using the first theory they used by deriving energy conservation law in order to get the height of the ball. And for the second theory, they considered the way of interpreting this phenomenon by collides the two waves into the standing waves and pumps the ball through this amplitude of this standing wave. And then they convert the height to the x velocity. So for the experiment part, first they consider the saturation of gas, which higher saturation is relatively hard to compress, therefore hard to create a standing wave and not enough air, which causes a lower height reach. However, if it's a too low saturation, there won't be a possibility for the air to compress and pump the ball. And also, they also analyze the distance between the objects. And using the energy consumption and anti-nodes will become less obvious. So then they investigate the initial release height of the ball and find out that it has a positive correlation between the height of the ball and the initial velocity. Since the lower initial height, the longer impact time and more energy consumption. So for the pros and cons, I think they have a clear graph for the theory and also include two different theories in the presentation so that they can compare the results of this theory and validates each other. And for the cons, they have vague explanation of the standing wave and lack of connection between the first theory and experiment, and also lack of display regarding experiment setup and phenomenon. So next, I would like to talk about the discussion point I would like to discuss later. First is the angle of launching, because they mentioned they use the height to measure the initial velocity. However, I believe that in every collision of the first ball that catapulted the second ball away, it actually creates an angle that might not be able to transfer into the vertical height that they are trying to measure. Therefore, and also, I think as we see in the experience setup, there's only one angle of looking at this launching ball. And I believe that if you're trying to analyze this initial velocity of this catapulted ball, you should have considered all three vectors. So they should have been multiple direction of the camera in order to capture this vectors of velocity. And also for the theory part, for the first theory, they used energy conservation law to derive the height. But I believe that the second ball, when the second ball is catapulted away, the air resistance actually provides an significant impact on this height. And also, there should be other energy consumption factors that occurs in the process. And also for other discussion point, I would like to more focus on how their experiments fits their theory, because I think they didn't elaborate this enough. So now, I would like to invite the reporter on the stage. So, for the first question, I would like to ask about how do you measure the height, since there will definitely be the angle of the ball launching upward.
We got it by selecting from a lot of data. So we only select the ones that go up vertically.
But that contradicts with the second one that I just mentioned, that due to the lack of point of view, you can only capture like two vectors. There should be another vectors to analysis. Although this might not be a significant impact to the velocity, I believe that this is a point that you should consider and improve in your experiment.
Thank you for the suggestion.
And next, I would like to talk about how you use the height to derive this initial velocity. Because I believe that once the ball leaves the catapult, it definitely, the air resistance definitely affects this ball, and air resistance is also proportional to the initial velocity. So I think you should have put air resistance into your consideration that this conservation of energy law would not be entirely correct due to that reason.
But we think that it's too small, and we think that it's small, so it's neglectable. The resistance is so
So
small.
I believe that if you're trying to prove that the effect of air resistance is slow, maybe you should have put it into a calculation and tell us that why it is negligible.
Okay.
So, and the next I would like to turn to the experiment page.
Which one?
First one.
Okay.
So, how do you think this this greatest rebound height fits in the theory you just mentioned? What theory does that affect? And what
The
parameters?
first one? Also, wait. Hold on a second. You can see that we have the X is for our saturation, which is 70%. Next. Final formula. So you can see that actually is over here, X. We actually put our saturation into the first theory. So that actually.
And how does it fit into the second? The
Uh,
standing wave.
We actually we use two theories because as for the second one, it's actually there's no variables that we can put it into this theory. So we come up with another theory for it.
Okay, I understand. May I use the blackboard? So I actually think that your second theory can also explain this phenomenon. That because you mentioned that this height or initial x velocity is determined by this amplitude. So if ball collides the cushion and the pressure inside the ball can actually affect how deep the ball will condense into the cushion, therefore determines the amplitude. So I think that's why how this saturation can fit into your second theory. Okay. So can I get to the second experiment? So here, you mentioned the distance between the two balls can affect x velocity. So can you also elaborate on it in order to use your theory to explain the experimental result?
So where's the blackboard? So because we're using static wave, so this is a cushion, and so we use a secondary static wave. So it would look like so this is cushion. So this is so you can see that it goes like this. Is that correct? So then and so the node is over here, okay? And then so the node is over here in the middle of in the center of the cushion. And so when we and so the distance we mean by over here from here to here. So that's that is an antennode to another antennode. So this is our distance between two objects. So we use this to calculate our wavelength of the sound.
Okay. So I would like to elaborate more on the question I just asked in the last discussion session. So I believe that standing wave created because if it collides with the cushion, the one wave will propagate through this side and one wave propagates through that side. And once it collides with each other, it forms standing wave. So is that what you're thinking about your theories?
Yes.
So I believe that the distance of this ball can actually determine the time gap problem that I just mentioned. That there's a probability that this wave traveling this side gets enough time to form a standing wave before this wave actually gets to the ball and flips it up. So I think this time gap should be a consideration in your theory. Time gap of this forming the.
Well, what about this one? The one's going here. it bounced back, I think that that there is enough time for it to bounce back and affect the result.
You mean
So-
the ones with longer distance?
Yes.
Yeah, so, I'm talking about the cases when the two balls distance are relatively close. So, I mean, to make your theory more complete, I think this is one of the relevant parameters you can consider. So, can I turn to the third experiment? Oh, sorry. So, actually I want the one with the material discussion. So, how do you think this material of cushion can affect this theory?
Okay, so as we can see that there is a slight bump over here during the collision, and if we change the material of the cushion, we might find that the situation, we can find a situation scenario that is actually flat, which does not create a standing wave. So that affects this experiment.
Specifically, I would like to ask about how it's affecting theory 2 about the standing.
You mean the material cushion?
Yes.
Okay, so
Like by explaining, pointing out the formula, the parameters, and the variables in the formula. You can use this to formula page of the theory 2 standing wave. What do you think the material affects the variables in the equation you provide? It's okay. So, in my opinion, I believe that because there's a frequency of the standing wave, and this frequency can actually be determined by this Young's modulus of the material of the cushion. So I think that angular frequency should be the reason why this material of the cushion can affects the x velocity. So, and I think also besides the material, there's another control parameters like temperature can slightly affects the modulus of this material. So, so maybe it's better to include these control parameters in the whole report to make it more complete.
Actually, we did use temperature, but I didn't present it in my presentation. So in the laboratory, we actually have air conditioning. So we always control it to like 25 degrees, the standard standard temperature. So we actually did the temperature. And for your first question, so what I was talking about is the energy consumption. Because different materials of cushion, they have different flexibility, right?
Yes.
So which actually affects the magnitude of the weight of the amplitude of the standing wave. So which causes energy consumption. So that is our perspective of this course.
I think you make a fair point. And this is my discussion session. Thank you.
Okay, thank you. For the update, please
So,
summarize.
I want to summarize the discussion. First, we discussed about the lack of point of view of the camera, so that the distribution of vectors can affect the x velocity. And also, we discussed about the air resistance can affect the height that it determined. So, we both agree that this should be considered into the theory. And also, we discussed how this saturation and affects the bending wave theory, which we conclude that this saturation can affect the amplitude of the standing wave. And we also discussed about this time gap between the two waves collides to become a standing wave. That our conclusion is that if the distance is long enough, this won't be a problem. However, if the two balls are close enough, this time gap should be considered into the theory. And we also lastly discover the material of the cushion. And that's everything. Thank you.
So, reviewer can please take the floor and ask questions to program.
So my first question is for both reporters and opponents. Did you mention the air resistance, am I right? So the air resistance is about the first floor or the second floor?
First,
First,
actually, both of them,
oh,
because they're so small that they can be neglectable.
and in your calculation is in, what did you think? The air resistance is about the first floor or second floor? You think you have to consider?
It's second floor, because the reporter used the height of the second floor to derive the x velocity.
Okay, and I want to ask you a question, in terms of the
Actually, it can't work, so you should just.
can you show me the page 23? So I think there's a tilting angle of your cushion, so did you consider the leverage in your theoretical model?
I actually said it would slide away, which means that
But
it's still, yes?
Whether slip or not, it is an tilting angle, so I think you should consider leverage. Did you agree with me?
So I think it has the same, it's pretty much the same as the standing way.
Okay, and so another question, did you consider about the shock wave? Did you think that shock wave is important?
I don't think it plays a significant role in this.
Okay, my next question is, how do you quantify the saturation?
We use the volume of the cushion that can contain. So then we actually have two cushions. The first one is to experiment on the 100% saturation. So which we pump gas into it until it explodes, so we know the volume inside, like the maximum it can contain.
I understand. So, my next question is, did you consider about the rotational energy of the ball?
Rotation energy?
Rotation. Did you consider it?
I don't think it's.
Because in my experiment, I observed that it was rotation too, but I'm not sure whether it was rotation in your experiment, so I'm curious about it.
Well, the data that I selected,
I mentioned the second ball. Did it?
I know.
Yes.
No, because we selected, we actually eliminate them, the ones that are rotating.
So you only.
We only pick the one which is still, which is not spinning.
Okay, time's up.
before and today's reviewer. Firstly, we talk about the air resistance, and the reporters say they consider both of the air resistance, and the opponents say they have to consider about the second most air resistance, and we agree with the opponents. We agree with opponents because we are consider about the exit velocity of the second pole. And the next one, okay, this is the summary of the reporters. So they discuss the variable of initial release height, saturation of gas, the distance between two objects in ship, and they use ruler to measure the height. Then they use tracker to measure the motion of a boat. And about theoretical, they use standing wave and they consider the pressure difference, the height, rebounding, and the initial mass. About reporters' performance, they have clear explanation, clear PPT, and a clear voice. However, they didn't explain the comparison between the theoretical value, the reason of the comparison of theoretical value and the experimental value, and there's no observation videos. Okay, next. About the summary of the opposition about the experimental, they talk about the three sides motions, three sides camera, and we agree with them. We think you have to consider all the sides of the motion. And another is that they talk about other parameters like air resistance, angle of longitude, and materials. And we also believe that the line on the caution will influence your experiments. About theoretical, they talk about the air resistance and the energy conservation and the standing wave. Next. And this is about opponents' performance. They have good combination and mention important questions. Next. And opponents' first question is the cushion didn't have flat surface, so it will affect, and we agree with the opponent that it will affect. Okay, about the material, yes, we also think we have to consider about the Young's module because we think it is important. Okay, about the shock weight, although they didn't explain about it, but I think we should consider about the shock weight in the cushion. So how did you measure the air pressure in the cushion? They say they pump in until it explodes. I think it is a good method because we haven't imagined it, but we think the accuracy we still have to measure. About the rotation, the reporter doesn't mention about the rotation, and I think the rotation is extremely important because in my experiment, the rotation it will rotate quickly and it will cause the energy. And this is all of my reports. Thank you for listening.
Thank you, opponent and reviewer. So we have two theories to explain the different scenarios and take many factors into consideration. And through the discussion, both the opponent and the reviewer, they all agree that only the marble, only air resistance only affects the marble. But in my opinion, actually also affects the baseball because we use NGH, which means that when it falls down, air resistance actually has a little bit effect on the baseball, which decreases its speed. But as I said, very very slightly. So which are in our opinion is still neglectable. And so we tried our best to minimize the inaccuracy, but the opponent said from the opponent the temperature and air pressure might affect the result. Therefore, there is still some room for improvements. And also, as for the shock wave, the reviewer said we discussed and think that it is not actually the effect of it is not significant, so it is still neglectable. Thank you for the opponents and the reviewers' suggestions. Thank you. We will improve. We will improve our experiments and do the factors they mentioned in further experiments. Thank you for your time.
Okay, thank you. A question for Gary?
Let's go to the result. You have the graph that shows the peak, two peaks.
Which one?
Peak.
You
The bouncing price, you have the two peaks.
So?
Yeah.
Okay.
Actually, I have a difficult to understand one thing. If you use the standing wave to explain it, standing wave means there's a peak there, then there's a notch there, then there's a peak, right? So there are two peaks, exactly good explanation. However, there's a knot there, but between the peak, there is no dot. It just goes a little bit down. Okay, how do you explain it, especially for the opponent first? Because you keep talking about the standing wave.
I believe that this lack of anti-node point of the standing wave is because maybe the experiment doesn't conduct enough samples in order to show the exact curve of this standing wave.
Okay. For the reporter, I have to ask you, did you really estimate the error bar?
How do you get your error bar?
Yeah.
Pardon?
How do you get your error bars for each data point?
It's from the claw that I mentioned. Because when we're adjusting the claw, it's very hard for us to to reach the exact height. So that's where the error bar came in.
Then I have the same question. Why there is a knot, it go down to zero between the two peaks?
That goes to the first theory. The first theory can answer that question. The first theory.
The first theory you propose.
You propose there is no propagation. Exactly bounce back. There is no correlation between the distance.
Do you show the correlation?
I mean, that is why it is not zero.
How about the reviewer? What's your point?
Pardon your question?
How about their stand? Do you have the different opinion? Because they keep talking about the standing wave. What's your opinion?
Your understanding about the standing wave that you mentioned here.
What is the problem?
Like, well,
If you have the standing wave, you have the peak of
No,
two peaks.
I'm talking about shock wave.
Yes. Why you propose shock wave?
I think that air induction have to be considered.
But shocker has another problem. Shock wave will propagate, go outside, right?
But the current is not too big enough to activate.
no question for the opponents. Then, well, so I have a question for three of you. Do you think the Young's module is important in this experiment?
Yes, I do think Young's module is important because it affects the frequency of the wave you just mentioned.
I'm not actually quite sure because we did not think about this.
Because they are mentioned about standing waves, so I think the Young's module will influence importantly because of the standing wave.
And since we still have time, so how about the time gap you mentioned? Why that is important for this experiment?
The idea I'm trying to express is that it actually spends a little of time to make this standing wave to form, which requires the two directions of wave to combine to each other. So if the two balls are close to each other, I think it doesn't have enough time to form this standing wave.
think the time gap is important, is 7?
I think it may affect a little, but I don't think that is quite significant.
I also agree with him that it should depend on the
Distance.
distance. Yes.
Thank you. Take the seats. And let's give the points to the recorder. 8,667. Okay. So for the opponent, 8,7,878. Okay. Then for the reviewer, 6,7,667. Okay. Thank you all.